Great. Hey, great to see everyone. So I'm going to give you all a demo of a kind of a X-ray helper package that I wrote called point collocation. And the background to this is I've been running a lot of hack weeks the last 2 years, and um, invariably about seems like most of the groups need to do a task that is a point collocation task. So they have points in space and time, and they need to find some remote sensing data that matches those points. So, for example, a group might have lat long time data for fish surveys in the ocean, and they want to find all the data from pace or SST, salinity, whatever, for those points. So they have this point collocation step that they need to do before they can get on to their science question. Their science question is definitely not point collocation. That's just a step that they need to do to get to what they want. And we've observed that groups in these five-day hack weeks can be spending 2 of their days wrestling with the point collocation task, and that's not what we want them to be doing. Um, and uh, if it were a simple point collocation task, it would be easy. But what we found is, when groups have many hundreds of points to match up, they're running into all kinds of problems, memory problems. Um, a lot of it's memory problems, or also just understanding how to do write the code for the point collocation. And my sort of fellow collaborator, Ryan Vandermeulen, we've been teaching these PACE hack weeks. And over time, we've created a lot of examples where we did a lot of big point collocation and figured out techniques to keep the memory under control, how to do things much faster than just kind of the blind, just sort of jumping in and doing it. And we wanted all our, during these events for people to be able to use those techniques, but not to have to know those techniques. We want that kind of under the hood. And I think, in spirit, this is a bit like, earthaccess, where, we used to give them like long, scripts to log in, and now they just do, authenticate or log in. All right. So I'm going to walk you through a few examples from the package. It is a intended as a helper for earthaccess right now. It is assuming that it's working with the output from earthaccess search. So it does use that results object. I did write it so that it could be used for other types of catalogs, although that wasn't the intent, really. Okay, so let's jump right in. So the package has 3 steps. You search, you need to find the granules that cover your points. So it's going to use earthaccess. And then you're going to come up with a plan. What granules are you using for each point? And it returns that plan to the user before doing the full extraction. And then we have the matchup task. I'm going to start with the quick start, which is a really simple example, and then I'll show you more complicated examples using like level 2 data or grouped net CDFs. So let's just see a simple example. Okay, I'm going to jump over here. Okay, so we're going to go to the quick start. Okay, so it's on PyPy. So we need to You don't have to log in ahead of time, but I have this in the tutorials because it is using earthaccess. The user does need to be able to log in. So that's why that's there. And okay, so first off, we need to get some points that we're going to match up. It needs lat, long, date. They don't have to be called that. That is the default. The user's in control of what things are called, but it does need lat, long, and a time column. All right, so we've got some points. We've got about 600 points, and the next step is we need to come up with a plan. So in this quick start, I'm going to assume the user is not yet familiar with what these files look like. So the first thing that they're going to do is just take a look at what the granule names are so they can come up with their plan. So here's the plan that you give the points, the data source. Right now there's only one data source with earthaccess. And then these are arguments we're passing to the data source. So we're going to pass in a short name. So let's go do that. So we got that plan. And so now the user is going to just check out what those granule names look like. So they need to scan to see what's here. So they're going to scan this. And after scanning that and probably doing a little research about what all these things are, they come up with a new plan, and that's going to filter on the file names and get the 4 kilometer data. So they're going to get monthly data, 4 kilometer. So let's run that one. So now we have a plan, and we're going to look at just the first few points, first 5 points here. So this, again, it's letting the user see what the plan is like so they can decide if this is what they want to do. And it tells them a summary. So we've got about 600 points, but there's only 4 unique granules associated with those points. These are so it's 4 unique points because these points are just probably 4 different months. We don't have any points that have no matches, and we don't have any points that have multiple matches. I'll show you examples later where that's not the case. So the user can kind of just sort of glance, do a sanity check here. They may also want to, before they commit to what they're doing, want to take a look at the data set. So they can open just one of the data sets just to get a sense of it. Again, they're trying to understand what they're about to do with the matchup. So it gives them some information about how it opened it. In this case, it used open data set and some info there. It tells it how the geolocation was auto-detected, and it found lat long, and that's what it's going to use. The user can change that if they want. And now we print that out. So now the user can look at this and see, aha, here's the data variable, RRS. Okay, it's got wavelength there. All right. So let's go ahead and get some matchup. So we're going to do 100 points so it's fast. And we're going to use the RRS variable there. Here we go. So this is going to take about a few seconds here. Okay, there we go. So I got 100 points in 20 seconds. And so that was good. We can look at what it returned, and it gives the lat long time that we started, and then it gives us some metadata. What was the granule ID it used? It tells us information about the granule time, the granule lat long. This again, just to make sure that you can compare those. Yeah, is it doing the right thing? And then it gives us our matchup data. So in this case, it did have wavelength also, so it pins that. We can pass in our data frame. I could have passed in wavelength and it would have picked specific wavelengths, but I didn't do that, so it appended all of them. All right. So that's kind of the basics of how it works. Next, I'm going to show you, well, first I'm going to pause, and then I'm going to show you a couple examples from some different, more maybe complicated examples. Okay. Wait. Great. Okay. So let's go ahead and let's check out, let's check out this one. So I basically, I went through the Cloud Cookbook and I found data sets that you guys were playing with and then used those. It's kind of come back here. Hey, okay. So let's see. We are going to get some sample points over the ocean. So I have these stored in the repository. So there we have about 50 points over the ocean. Let's see where they're located. Okay, there they are, all over the ocean, around the world. And so now we're going to develop a granular plan and take a look at that. Okay, so what do we see here? So 52 points, 52 unique granules. Okay, so we've got 52 points and there's going to be 52 different files. Okay, so this is probably going to take a little longer, definitely, than that quick start one. Kind of look at this, scan this. All right, let's say it looks okay. If we wanted, we could look at the results here. This is the earthaccess results. We can take a look at what the data looks like. And we can see, okay, we got these coordinates. We have these data variables. And we can look here, we can see it auto-detected longitude and latitude. All right. That's what a plot would look like. This is SSH. And now we can go ahead and get the matchups. So there we go. This one's going to take about 18 seconds again. Okay, 16 seconds. Okay, here we go. And there we go. So now we have our lat long, and I dropped everything else just to, show the matchup. So showing it's got those matchups here. I do a few more examples with temperature. Again, this is a, I wanted to show you, so it can also work with three-dimensional variables. In this case, lat long depth. That quick start was also three-dimensional, so wavelength. So I could also include wavelength in the data that I'm sending it. But let's see how this works, say, for temperature. What I'm going to do is I'm going to pick a depth in here, 1,000, I think that's 1,000 meters below. And so I add that to the data frame. And now what you have to do is tell the plan that you're adding another coordinate. So you add it to this thing called chord spec, and then you tell it in the source, it's called Z, and in the points data frame, I called it depth. So that's how that works. Okay, so I'm getting temperature and salinity. It's a different data set that has this depth in it. So we can, take a look at that, and you can see it's got that depth. And now we can get the matchups. So I'm not going to run this one because it is 44 seconds, but you can see it's the same idea. I tell it the variable, and then I need to pass it this special chord spec because I am adding on a new coordinate, which is depth. If I were adding on wavelength, the same idea, I'd send in the chord spec and I'd specify that an extra coordinate is wavelength.
All right. So now I'm going to show you a couple more examples, two more, little more sort of unique. The first one is still level 3, and then the next one I'll show is a level 2. So I'm going to show ISAT 2 level 3. So what's unique about this is that it is polar. So let's go get some points. So these are points that I generated over the pole. And let's go ahead and we'll just see what this looks like. Yeah. So here you can see we're over the poles. And I'm going to be matching up to that data that you see here. And one thing that points collocation does is that you can use different types of distance metrics. So if you are getting nearest in the poles, you don't want to use just plain old the default method. You want to use a haver It's one of them that you can use. It's a really standard one. Distance metric so that you get proper distances when you're right up here near the poles. Similarly, if you were getting distance metrics, if you're right near the where it's changing from -80 to 180, you'd also want that. Okay, so so I got these are points, they're up in the latitude. And so same thing, I can go, tell it the ISAT ATLO 21. So go get that plan. And so I've got 50 points, 33 unique files. Points with 0 matches, 8. Well, you saw that some of them were over land, and the product is not, this particular product's not over land. So those would be ones that are over land. So it just says there's no matches. We can look at it, and I didn't actually have to say open method equals data tree. It would be kind of intelligent and suggest using data tree. But I happen to know that I know that it's grouped, so I'm going to use that. Okay, it's taking its time here. Okay. Yeah, okay. So what you can see here is by opening it up, you can see that it's grouped. And now I can poke around at this and figure out which of these groups I need to merge. And so in this case, when you're working with a NetCDF where you need to do some merging, you create an open method profile. So I tell it, hey, use dataset. It's faster than data tree. And then I'm going to merge on the base, and I'm going to merge on monthly. I also notice as I'm poking around in the file that it has some unique names for the chords. So I need to tell it that. It's the CF X-ray won't automatically find these. So I tell it lat is called grid lat, lon is called that. I can pass in some arguments to the open. I pass it this just to quiet a warning. And I can then pass that open method to the open dataset just to check that the file looks okay. And what it would show is this. So at this point, I can see, great, I've got these things in my coordinates. That's what I want. I can check here what the variables are. And now I can go ahead and do my matchup. So here we go. So I'm going to use that open method that's telling it what groups to merge. Here's the variables I want. And I can tell it the spatial method, and I can tell it that haver sign. I'm not going to run this. You can see it takes 1 minute and 46 seconds. These particular files take a long time to open. But it's doing all the nice things in the background, and we'll get those matchups for me. And then this is what it gets out after that, 2 minutes of time. It gets those matchups for me. All right. The last one I want to show you is level 2.
And I've got a few different examples of level 2, like the tempo, that's a level 2. But I'm going to show you pace because their level 2 granules tend to open a bit faster. So the level 2 data, this in the workshops or in the hack weeks, like our students just give up on level 2. They just can't do matchups with them. It's way too hard. So I'm hoping like with this package, they can work with level 2 data sets the same as the level 3, and they don't have to think about all the little things you have to do. It's just going to work the same way. So we're going to get some level 2, short name. Okay, this is just printing off some short names. Okay, so I'm going to get some data points here. Again, I get my 500, 600 data points, and I'm going to get this ocean color level 2 AOP product. So this is kind of a unique thing, this time buffer for level 2 data. So if you looked at the metadata for the level 2, it's a really short time window. And the user needs to decide like how close in time they want to be. And in this case, I'm going to match up points that are within 12 hours of when that swath data are. So that's what's going on here. All right, so there, came up with a plan. We can look at it. You see, this is so much easier for our users. Like, boom, they've got a plan. It tells them which of the level 2 granules it's going to open. You can see in this case, there are 2 different ones that it's opening. And that's okay. It's going to come when it returns the results. It'll have the matchups. It'll have 2 different rows. The users can decide if they want to average those or pick one of them. They can take a look at the file. That'll probably take a little while. Oh, that didn't take that long. Okay, here we go. So now they can see the file. They can see the different groups. And they create that plan. They want to merge the geophysical and the navigation data. Boom. Okay, so there. Now they can see they've got their coordinates. They've got their variables. Yep. That's what they want it to look like. And now they can go ahead and get their level 2 matchups. So they are getting, in this case, 600 points, level 2 matchups. And you saw there, it takes about 43 seconds. Again, like this particular task, getting these level 2 matchups, like I said, it turned out to be basically impossible for most of our teams to work out in the time they had allotted during hack weeks. All right, I'm going to stop there. And if you go to the website here, I did, open up in Colab. You can open all of them in Colab. I will warn you, be getting data from AWS, from Colab, which is not an AWS. It is quite a bit slower, but everything works.
I noticed you, good time for questions?
Yeah.
Okay, cool. I noticed you had a 2 gigabyte memory Jupyter Hub instance. That's pretty awesome. I was curious about, hold on, I wrote this down. You mentioned using a different distance metric for polar data. I guess that only applies if this polar data is in a non-polar projection to like compensate for the stretched kind of perspective of data that might be in lat-long projection or coordinate reference system.
Yeah. So correct. It is assuming it's a non-corrected projection, and that Haversine is doing that correction for you, or it's doing that transformation for you.
Okay, cool. Thanks.
Yeah, I guess that's on the to-do to figure out how to check the what projection the data are in.
Yeah, like you're thinking like to automatically select that spatial method for the user so they don't need to know?
Yeah, possibly. Yeah.
Okay, cool. I have another question, but I see Andy has his hand up.
Yep.
Hey, Eli, this is great.
Yeah.
So I guess this is related to Matt's question. So it looks as if you're searching for the points in latitude, longitude space, right?
Mhm.
That's great. Using the haversine and everything. I'm just wondering whether you considered or tested converting the points to the projected coordinates and then using X-rays vector selection to be able to pull the points from the granules, which I think would probably be a lot faster because you're not needing to do that nearest neighbor search. You can just work in the rows and columns.
So, um, I have definitely done that before. And the package does use X-ray. So X-ray has a new like indie points method, which I think might do that. It's for let's see, let me search it up. X-ray. Well, index for irregular indimensional data. I'm not sure if that's what you mean.
No, it's so if you in X-ray when you do a selection, if you convert it, it's kind of nuanced, but because you're doing everything under the hood, it wouldn't matter. You can pass your points, the X and Y or latitude, longitude coordinates as a data array to the dot cell method, and that will do a vectorized search of the grid. So it will return a value for every single one of those points in that grid. So
mm,
it's I can send you a tutorial or a short example of how to do that, but I would imagine that that's a lot faster, and you could and it might even be that Rio X-ray has that
mhm.
method built in. But that I
Yeah,
mean
send me.
that would speed things up, I think.
Yeah.
But that does assume that the you would either have to supply the coordinate reference system or X-ray would have to be able to find that within the NetCDF or HDF. And
Hmm.
if everything's been built properly, it should be able to do that. I mean, meaning the file has been constructed properly, but that's not always the case, as you saw. Embarrassingly, there's people use grid lat, grid long rather than latitude and
Yeah.
longitude, which is not CF compliant. So I think, but that might actually speed things up. And I really
Yeah.
like the way that you can circumvent that by providing the structure of the data set with that dictionary.
Hmm.
That's really good. But yeah, that was
Yeah.
that
Yeah.
was that was one
Yeah.
thought that occurred to me.
Yeah. Send me the tutorial, although I'm pretty sure that under the hood, that is how it's doing it. It is passing in a data array of the
Right.
points. Um, and so it is doing that. Um, but I would still like to look at your tutorial to see if there are any kind of extra tweaks, but it is like those kinds of things that are those kind of impossible to teach our students, and we didn't want them to be thinking about. We just wanted that
Right.
kind of best practices to be happening under the hood.
Completely agree. Yeah.
Just wanted to interject really quick. We're a few minutes over. I'm happy to keep this going. I just wanted to let folks know in case they needed to drop.
Yeah, I mean, I can take like one more question and then I should drop off to my next meeting.
Cool. And if anybody else has a question, I've already asked one, so I want to make sure I'm not taking the last slot. Okay. So first, I just wanted to kind of like validate my understanding of what's happening here when we're doing point collocation, make sure like I fully get it. You've got some points maybe representing weather stations or buoys or something, and you want to enrich the data you already have for those points with data that's available in a raster data set. So you're looking for the single grid cell that corresponds with that point from your raster data set to get that value and enrich your point. Is that right?
It might be swath data. It doesn't have to be a regular grid. A raster, I think of it as a regular grid, but this definitely does not need to be a regular grid.
Okay, so some sort of grid.
Some kind of
And
grid.
you're expecting it to intersect with exactly one cell in that grid. Is that right?
Yes, all these methods return one match.
Okay. All right. And then the question that I was getting to was when you're using under the hood, you're using Xarray to do all of the access. So if the data is in like a cloud optimized format, then Xarray could handle, for example, only range getting exactly the point you want. So in some cases, depending on the data that you're accessing with Xarray, you might see better performance, and that's your library doesn't have that complexity. It's all just managed by Xarray. Is that right?
Yes, it's all managed with X-ray, and right now, like I said, it's using earthaccess, which is opening those files and setting up all this stuff it needs to be able to access cloud data.
Okay, cool. So like earthaccess.open as opposed to xarray.open dataset, or
it does. It creates the file set with earthaccess open, and then it passes that file set to Xarray open.
Okay, got it. Yeah. Thanks.
And it only opens the number of granules that it needs. So the part of that plan is that if you have a whole bunch of points that are associated with one granule, it's only going to open that granule once.
Yeah, okay. This is really cool. Thank you for showing us.
Yeah, and like it's using the results from earthaccess. So if earthaccess, like I'm thinking like in the future, say if you could put in like a collection and earthaccess would point you to a virtualizer, and then I think the point collocation would then use that result and use that new thing. Yeah, so it doesn't do any of the logic around like, hey, how do I open this? How do I give this the right information to open? It is assuming that your data access thing is taking care of that for you. So it would be like I've thought too about like making another data source be Copernicus Marine. And Copernicus Marine does kind of the same kind of thing. Like it takes care of like setting things up so that you can open their data. I'm not sure I'm going to do that though. I kind of think right now I'm just focusing on earthaccess.
I got a quick question. So I'm curious about the plan. Like, what is the intention of the plan? Like, I guess I understand like, let's match these data sets, and you find some granules, and then you extract the point from, but it's just like an intermediate, like before you fetch the data, this is what the package will do, and you think that scientists will say like, oh, I don't know, what would be the goal of the plan? Yeah.
So, for example, am I still sharing my screen?
Mhm.
Yes.
Yeah, so like, here's the pace level 3. Oops. Many files here. Okay, so like here would be an example, and the user's like, oh, hey, I want to match up to this product. Great, and they just put that in there, and what they don't realize is that there are like 16 different granules associated in that collection. Like there's these rolling 32 days, there's a seasonal thing, there's an 8-day, there's a daily, there's a monthly. And if they ran the plan here using that, and they took a peek at it before they run the matchup, they would see, oh my God, this one point has 16 different granules associated with it. So you want them to see that before they go ahead and run it.
So it is more like a preview of what granules, but not in the sense of like a query planner or that kind of like. It's more like a semantically kind of a preview of the mapping, I guess, right?
It's developing the mapping, and the user can look at that if they want. They don't have to. They could just run it. But what it's doing is it's getting the results from earthaccess, and then it's looking, let's say, there's, 30,000 granules from that result. And then it's saying, okay, which of those granules has my data points? And it's like, okay, it's 4 granules that I'm going to need. And okay, so this granule, how many points are associated with that granule? Okay, 100 of them are associated with that granule. So it's got to figure out, because it doesn't want to open up more granules than it needs to. So the plan, it has to do the plan to know, okay, I'm going to open that granule and I'm going to get the data for these 100 points. And then I'm going to open up the second granule and then I'm going to get the data for 10 points there. So that's what the plan is used for. Like you wouldn't want to go and say, okay, let's go through each point one by one. That would be super inefficient. You would end up opening way more files than you needed to.
Nice.
I will also note, Matt kind of noted this, that I'm on a puny, I'm kind of maxing it out here right now because I was making images, plots. But, making sure the memory doesn't explode, that took a lot of work. Just making sure things are really, really closed down before moving on to the next granule. That's been a hard thing to make happen. Not hard, it just had to be very careful. And if there's any place where the memory starts leaking, then it just starts building up, and eventually it crashes the machine.
One observation, I think you mentioned it at the end, that if we were to use virtualized collections, this will be way, way, way faster and more efficient, right? Because you only need the indexes for the chunks that you care about. So you have the grid already available. So.
Yeah.
I'm going to go ahead and stop recording.
Yep.
This was fantastic.